All right, everybody, I think we're about to get started. So if you want to grab another slice of pizza or a beverage or a t-shirt, do so now. Otherwise, you're going to have to sit and listen to me for the next hour or so. So I apologize for that in advance. I think I'm just not going to use this. All right, so thank you all for coming out to the Meetup. The title of this talk is the PyData Toolbox. My name is Scott Sanderson. You can find me on various social media here. You'll also be able to find the notebooks and slides and other talk materials for this talk on my GitHub, github.com/ssanderson/PyData-toolbox. And I'm also Scott or ssanderson at quantopian.com if you're looking for other ways to contact me. Now that I just gave that, here's the actual slide about me. So I'm a senior engineer at Quantopian. Quantopian is a company that builds a platform for people to write algorithmic trading strategies. We provide all kinds of tools to backtest and research and live trade and do all the kinds of things that you need to do to develop a trading strategy. And then we provide education and a platform and lots of other cool things. So if you're interested in any of that stuff, which if you're at this meetup, you probably are, definitely check that out. My academic background is actually in mathematics and philosophy, and I kind of stumbled backwards into computer science through an interest in video game programming, and then after that, stumbled further into quantitative finance. And again, these are places where you can find me. So the outline of this talk is kind of the premise of this talk was that I've been around at PyData and SciPy and PyCon and all these other conferences, and seeing all sorts of like cool, fancy new frameworks in the PyData space. There's all these like expression things and compiled libraries and big data and Hadoop and all this cool stuff. And that stuff's all great and awesome. But one of the things that I think is important when you're looking at any of those tools is that before you go to sort of a fancy, complex tool, you should understand kind of the building blocks for those tools and understand the foundations of the stack that you're working with. So the idea of this talk is actually to be sort of, not exactly, it is to be an introduction and then sort of intermediate steps towards understanding kind of what I see as the core libraries for doing numerical computing in Python. So the outline is sort of going to be built around the various data structures that are parts of those core libraries and the kinds of operations that they provide and the kinds of problems that they're trying to solve. So to start with, to have sort of a point of comparison, we're going to start by talking about Python's built-in data structures, in particular the built-in list and dictionary data structures, what they're good at, what they're not good at. And we're going to talk about sort of what are the problems that come out of Python's execution model when you're trying to do large-scale numerical computing. As a result of that, we're going to end up looking at the Numpy library and understanding how Numpy tries to address some of the challenges that come out of sort of standard Python. And then after sort of looking at Numpy and understanding how it works, we're going to move on to Pandas, which is kind of a higher level tabular data structure library that's built on top of Numpy. And at the end, we're going to look at some sort of standard, or not standard, but some sort of more data science-y things with some real world data. That's kind of the backbone of this talk. So if you've seen me give a talk before, you've probably seen this quote up. So this is by Rob Pike, who is one of the founding fathers of Unix and is now the designer of the Go programming language at Google. But before working on Go, he wrote a lot of C. And he wrote this essay called Notes on Programming in C with all these sort of rules for how you should think about programming in C. And one of the ones that sort of resonates with me is this one. So it says, Rule 5, data dominates. If you've chosen the right data structures and organized things well, the algorithms will almost always be self-evident. Data structures, not algorithms, are central to programming. And so the idea here, right, is that we write algorithms, we do all these things in programming, and often the right way to organize at least certain domains in programming is around data structures, right? Arrays and lists and dictionaries and all these other things. And there's many algorithms which, if you choose the data structures right, the algorithm sort of writes itself, right? But the tricky piece was understanding how to map your problem onto the data structure, or how to choose the data structure in a way that expresses your problem. And that's going to be kind of a theme as we go through this talk. So first off, lists. We're making sure that I ran my first cell because, oops, there we go. Cool, we did that. So Python lists, right? We put square brackets around them. We can put things in them. lists are indexed containers of heterogeneous data. So we can hold integers in them, we can hold strings in them, we can hold floating point values in these, we can hold, arbitrary Python values in these. Python calls these lists, pretty much every other programming language in the world calls these vectors, but a Python list is not a linked list, it's a vector. It's efficient to append to it, it's not efficient to insert to the front. Lists in Python are zero index, so if I do L square bracket 0, it gives me the first element. If I do L square bracket 1, it gives me the last element, or the second element. A little more interesting, Python has this sort of sugar where if you index with a negative number, then we start indexing from the back of the list. So if I do L bracket -1, that gives me the last element of the list. And if I do L bracket -2, I get the second to last element of the list. And I eventually go back to negative the length of the list. Eventually, I'll overflow past the end of the list. Oh, I threw that extra object in there. Another sort of neat feature of Python lists is they support this slicing syntax. So if I do L bracket index colon index, that says take a copy out of the list from the values starting at the start index inclusive and stopping at the stops index exclusive. So that preserves the property that if I subtract them, that's the number of elements I get back. So if I do L1 colon 3, that's going to give me the values at indices 1 and 2. So in this case, I get string 2 and 3.0. I don't have to include the first and last elements there. So if I just do colon 3, that's equivalent to 0 colon 3. So this is give me the first 3 elements of the list. And similarly, I can do 3 colon, and that says give me everything after 3, or from 3 and afterwards, rather. Those things are relatively well known. I think even less well known is there's actually a third possible thing you can slice by, which is a step. So if I do 1 colon 7 colon 2, it says start at 7, start at 1, go until 7, and increment in steps of 2. So this is giving me every other element out of the list, starting at 1, going until 7. So you can see here I started at 1, then I skipped over C, went to D, skipped over E, went to F, and then presumably F or G is 7. Lists are size mutable, so I can append to a list in relatively efficiently. It will periodically resize and make a copy of the array, but amortized over doing lots of appends are relatively cheap. And this will be in contrast to some of the data structures we're going to see later, where appending or changing the size is not a cheap operation, or not even a supported operation at all. One of the other sort of cool things about Python is that it has this list comprehension syntax. So if I have a list, 1, 2, 3, 4, 5, then if I do some expression for some name binding in L that says take my list and produce a new list by calculating this expression on every element of the list. So here I'm saying take this list and double every value in it by multiplying it by 2. And this is sort of a common thing that we want to do, right? We have a list of things. We want to do something to every element in that list. Particularly when we're doing numerical computing, we very often want to do things like multiply a vector by 2, or multiply 2 vectors together, or do something on every element of an array. And if we're working with lots of data and lots of numbers, we care about that operation being fast. So just to review, Python list is a zero index sequence of arbitrary Python values. We have slicing syntax, which is start, stop, step. We have efficient O1 appends and removes from the ends. I didn't show removing, but you can do pop to get an element off the list. And comprehension syntax lets us map expressions over a list with a nice syntax. Python dictionaries are sort of the other very commonly used data structure in Python. So dictionaries are key value mappings, the sort you would see in like JavaScript or in PHP associative arrays or anything like that. So here I have a mapping from philosophers' first names to their last names. So we're mapping David to Hume and Immanuel to Kant and Bertrand to Russell. And I can look up values out of this.
Guys, going back to the list, does it support X and Y access if you get an array of?
The list object does not support that natively. Yeah, so Python does not have features in the way that like Fortran does, for example, where I can natively say like add a list to a list, or like slice a column out of a nested list or something like that. A list inside of a list is just a value. Because I could have a list that contained a list but then had a string, for example, or had an integer or whatever else. It's just a container of stuff. So that's another feature that we may be interested in moving forward. Dictionaries, I can add things to them. So again, these are efficiently sized mutable. So I can add Wittgenstein to our list of interesting philosophers. And I can delete David Hume if I feel like he's not actually that exciting. There's no notion of slicing on dictionaries because dictionaries are unordered. So what you might want this to mean would be something like, if a dictionary had a notion of order on its keys, then give me the values between the key Bertrand and the key Emmanuel. But Python's dictionaries are semantically unordered, so this doesn't mean anything. And so the error we get here is actually telling us that it's trying to hash the slice object that I'm indexing with, because that's not a valid thing to do. So again, to review, dictionaries are unordered key value mappings from almost arbitrary keys to arbitrary values. The one additional restriction on keys is that they have to be hashable, which for the most part means immutable, and someone has to have implemented a hash function. They support efficient, meaning amortized order 1 or constant time, lookup, insertion, and deletion. And there's no notion of slicing or ordering on these. So great, right? We've got Python has sort of the standard set of data structures that you would expect from a modern language these days. You know, lists and dictionaries, and we've got some other ones, but for the most part, you know, if you have lists and dictionaries, you can write most code that you'd want to write on a day-to-day basis. So we might be like, what's the problem here? Well, suppose we've got some matrices, right? So here, as was suggested, I'm representing matrices as lists of lists, right? And this isn't anything that's natively supported by Python, but obviously, if I have n dimension, you know, if I want an array of arrays, I can just represent this as a list of lists, and it works perfectly fine. And say I want to write a matrix multiply algorithm. So if you're looking at this and you're sort of feeling sort of queasy and sad and kind of confused, you're having the right reaction to this. So this is, you know, it works, and if you stare at it and think about it for long enough, you probably convince yourself this is correct. But this isn't the nice sort of pleasant, you know, easy to read. Python sort of famously prides itself on being easy to read, and I would argue that this is, you know, pretty unpleasant to read Python code. But so whatever, that's fine. Sometimes we're willing to make sacrifices, you know, to readability in exchange for performance. So yeah, so you know, Clint Eastwood might not be super excited about that. So probably the more important question if we're doing numerical computing is how fast is this? So we had relatively small matrices there. If we time our matmul, so this is using the % time magic in the Jupyter notebook. I'm actually in a Jupyter notebook right now. It's just a fancy Jupyter notebook that knows how to be a slideshow as well. So that was fine. You know, we ran that matrix multiplication in 28 microseconds, which I don't really have a great intuitive sense of how long that is. If I had Grace Hopper here with some wires, maybe I could figure that out a little better, but I don't have a good sense of that by myself. So here's a function to make a random matrix of a given size for me, right? So it says, give me a random m by n matrix, and if I make, say, a 2 by 3 matrix, then I get this. So what happens if we try to do our matrix multiply on a 300 by 100 and a 100 by 300 matrix? Okay, so that took 1.4 seconds, which is not great, but you know, maybe that's acceptable. So let's see how this scales. So say I kick this up to 100 by 600. 5.88 seconds. So not scaling well, right? This is not what we want if we're trying to, you know, do, say, you know, long-short equity strategies where we're looking at, you know, hundreds of days worth of pricing data, or God forbid we're looking at minutely data and we're looking at, you know, hundreds to thousands of stocks, right? This is not going to complete in any reasonable amount of time for us. But maybe that's just, you know, the fast that computers can possibly compute this thing, right? There's no reason to believe that just because this is slow that it could be faster. So let's look at a little bit of a simpler case. So here's a dot product implemented in Python. So I'm saying, given a list of x's, which I'm going to assume to be a list of integers or floats, and a list of y's, which I'm going to be assumed to be the same length, I'm going to say sum of x times y for x, comma y, and zip of x's and y's. So I'm just iterating over both of the lists at the same time, multiplying all the values and adding them all up. This is actually sort of relatively nice, readable Python. And we're going to compare that to Fortran. So Fortran is sort of the gold standard in high-performance numerical computing here. So here's a dot product written in Fortran. So again, we're going to take an array of x's and an array of y's, and we're going to take a result parameter that we're actually going to write into, because that's a more common idiom in Fortran. And then we have to tell Fortran all this stuff about our values. So Our values are going to be double precision floating point values, and we're going to have them be intent in, which means they're inputs. And this one's going to be an intent output, and this one's going to be an integer. The actual algorithm is still quite nice, right? We have sum as a built-in, and we actually have array times array as a built-in notion in Fortran, which is kind of cool, right? So I can do element-wise multiplication on arrays as a native syntactic feature. Huh? So zip says if I have 2 lists of the same length, if I zip them together, then that gives me a single list of the same length where all the elements are pairs that were drawn from the original list. So it converts a pair of lists into a list of pairs, or more generally, a tuple of, and I can pass multiple things to zip. So I give it 3 lists, then I would get a list of 3 tuples, for example. And I'm, again, using the %% Fortran magic, which is, this is not built into the notebook, but it's a package that you can install. And this is compiling this function with f2pi and throwing in a temporary thing. This is not how you'd actually want to run Fortran from Python if you wanted to. But it is using the library that you might do it with. And the underlying pieces here are essentially the same thing that you would use, or that like SciPy uses to bind Fortran, for example. So we're just going to make a list of 100,000 floats. And then a little foreshadowing here, we're going to make a Numpy array of that same data because we're going to use that to pass to Fortran. And so our question here is how much, how slow is Python compared to sort of the gold standard, which is Fortran? So our Python dot product on 100,000 elements is 7.18 milliseconds. So that could be good, that could be bad. I don't really have any sense of that. Our Fortran dot product runs in 1.3 microseconds. So we're on the order of like 40 to 50 times slower than Fortran. This is actually better than I thought it would be, to be honest, for Python. This is not that bad of a result to be only 40 times slower than Fortran. But nevertheless, if we're caring about numerical computing performance, we might say, well, geez, if there's something that's 40 times better than what we're doing right now, like, why are we using Python for this kind of stuff? So yeah, Python, right? This is how we feel when we're using Python when we could be using, say, C or Fortran or an array computing language, right? We're just slowly multiplying our matrix. So the question we should ask ourselves, right, is why is the Python version so much slower than the Fortran version? Like, we might think, well, there's nothing inherent about one language that should make it faster than the other. What is it about? What are the choices that Python has made that have caused it to be slower? There's nothing magic about Fortran. So one of the things that is making Python slower is the fact that Python's dynamically typed. So in Fortran, there's a type associated with every name in your program, right? If we go back to that, if we go back to our Fortran code here, right, I had to say that x's was an array of double precision floating point values, and y's was an array of double precision floating point values. The result was an array of double precision floating point values. And the compiler can verify that I didn't, assign an integer to a float or something like that. So it doesn't have to emit instructions that run at runtime in order to verify those facts, right? It can just say, I've got floating point things. I know I have floating point things. I'm just going to run those instructions.
What is the I in this function? Or is that just?
That is left over from a previous implementation. We don't need that. It's probably getting optimized out by the Fortran compiler because we have a compiler and it can do things like detect unused variables and not do them, right? So one of the benefits we get of having a statically typed language and a compiler is that someone has looked at all of our code and analyzed it and decided here are only the bare necessities that you need to do things at runtime. We don't have that luxury in Python, right? So in Python, here's again sort of a dot product. And I'm going to do mul element-wise, and I'm going to pass one array, which is a list of integers. So it's 1, 2, 3, 4. But then over here, I'm actually going to pass a whole bunch of different stuff. So I've got an integer. I've got a complex number here. So 2 plus 0j. It's 2, but 2 is a complex number. 3.0 is now a float instead of just a regular integer. And I also just have the string 4, which you might not even think would work to multiply. But it turns out that integer times string in Python means repeat the string the number of times equal to the integer. So if I mul element-wise these two lists, then I get 1, and 4 is a complex number, and 9, and 4, 4, 4, 4. And if we think about what must have happened here, right, Python had to look at every pair of elements that I was performing this multiply operation on and decide what was the right operation to do there, because the code that you need to execute to multiply two integers is very different than the code that you need to execute to repeat a string 4 times, right? So there's some sort of dynamic type checking happening every time I do a multiplication operation. And we might think, well, that's going to take some time, right? So that's the first thing. The second thing, which is kind of related but distinct, is Python's an interpreted language, right? So it is compiled in the sense that when you take source code, it's compiled into an intermediate language, which is the bytecode. But then there's an interpreter that takes the instructions from that bytecode and basically sits in a big switch case and says, all right, what instruction is it? Okay, I'm going to do that instruction. Okay, what instruction is it? I'm going to do that instruction. What instruction is it? I'm going to do that over and over and over. And we can actually use Python's built-ins to look at this. So here's a very simple expression. I'm doing A plus B times C. And if I compile this and then throw this into the dis module, which is the built-in disassembly module, I can see these are the instructions that Python's going to emit. So it's going to say, load the name A, load the name B, load the name C, binary multiply, which is going to pop B and C off of a stack and multiply them together and then push them back onto the stack. And then it's going to do binary add to add the resulting value on the stack to A. And so there's literally going to be a loop in C that's going to sit and read these instructions one at a time and decide how to do them. And we can go look at that. So CPython is just a program like any other program, and it has source code. So here we're in ceval.c, which is sort of the beating heart of the CPython interpreter. And you can see we're just in this giant switch case, right? So we're switching on, here's the instruction, and there's just stuff, right? And there's a lot of stuff. It's a whole bunch of stuff. So binary add was the thing that we were interested in there. So what happens when Python decides, hey, I need to add two things, or I'm going to execute the add instruction? So the first thing that we do is check if either of them are Unicode. And then if so, we're going to concatenate them. So that's just a special case that's built in. Anytime you add anything, the first thing Python does is say, are both of these Unicode? And if so, I'm going to special case that. And then if that's not the case, then we're going to call this PyNumberAdd function. And PyNumberAdd is going to go grab a function pointer out of the type of the object, and it's going to dispatch that. It's going to do all this stuff. We're going to do like 15-odd pointer chases and a whole bunch of other things, just because we wanted to add two integers, right? This is sort of an insane amount of overhead if you think about it too hard for what's actually happening here. So given all that, we should actually be like pretty impressed that Python's only 40 times slower than Fortran. Like the equivalent in Fortran was like one machine word, one machine instruction. It's kind of staggering actually that Python is as fast as it is given the way that it works. So to summarize, why is the Python version so slow? Well, dynamic typing means that every single operation we do requires dispatching on the integer type. We say, are you an integer? Okay, are you still an integer? Are you still an integer? Yep, still an integer. And then having the interpreter means that every instruction is dynamically fetched and dispatched at runtime. And there's some other overhead. So like Python integers are actually arbitrary size, which imposes some overhead. We also have things like a garbage collector, which means we have to keep track of who's seen what objects and make sure that they don't actually accidentally get garbage collected, but that they do get garbage collected when we want them to. And there's overhead associated with all these things. So this is a quote from Jake Vanderplas's 2015 PyCon talk, which is part of the inspiration for this talk. It's one of my favorite talks of all time. I wholeheartedly recommend you see it. So Jake says, this is the paradox that we have to work with when we're doing scientific or numerically intensive Python. What makes Python fast for development, this high-level interpreted and dynamically typed aspect of the language, is exactly what makes it slow for code execution. So what do we do, right? We have this language, we like this language, it's got all these cool features, but it's slow if you're doing lots and lots of numerical operations. So one thing we can do is flee, right? We can go live in Fortran and live the rest of our days as like, assembly programmers, right? And probably would feel like we're back in the Monty Python days. Another thing we can do is just accept our fate, right? This is fine. This is the world we live in. We're just going to have our code run slow and maybe hope that Moore's law eventually saves us. But we might think that, well, there's something we can do about this, right? So we said that the reason Python is slow for numerical computation is because it performs dynamic dispatch on every operation that we perform. But a lot of the time, we don't want to do different things in the loop, right? We have a loop where we're doing the exact same thing, and we expect to have the exact same data at every iteration of that loop. And so we're dynamically dispatching over and over and over to do the same thing every time, and that's wasteful. So if we don't need Python's dynamicism, can we find a way to not pay for it, at least not pay much for it? So here's the idea. Here's sort of the one big idea in all the SciPy stack. Can we dispatch once per operation instead of once per element, right? Can we just say, okay, I've got an array of integers. I'm going to verify that fact once and then do something on the whole array, right? And I don't have to look at every single element of the array. I don't have to pay a constant overhead in the size of the array, just a constant overhead in the fact that I have arrays. This is sort of the one thing that can save us, as it turns out. So this is where Numpy comes in. So Numpy is a library implemented in Python. A lot of the guts of it are implemented in C, and it turns out one of the reasons that Python is a popular language for scientific computing, despite all the things we just talked about, is that Python has a really good C API that makes it really easy to write core data structures that are implemented efficiently in C, but still exposed to users as native types, or sort of like native feeling types. So here I've got a NumPy array. I'm initializing it with a list, and NumPy is going to look at this thing and recognize that all of the values in my list are integers. And so if I look at its D type, for example, it's going to say this is a list, or this is an array of D type int64. And I will only accept int64s, and if you try to put something else in me, I'm going to barf. And that's going to allow us to do some nice things. Another thing we can do is, rather than, say, looping over our arrays every time we want to do some operation, we can just define what it means to add two arrays together, because Python, because it's so dynamic, has a lot of flexible tools for overloading operators. So I can say, as the author of NumPy, overload what it means to add two arrays together by implementing the special _add method. So if I add two arrays together, that says, okay, line up those arrays and add them together element-wise. That sort of binary operator works the same for lots of things. So I can do array times array. That's going to element-wise multiply them. And there's also lots of methods on array, like sum or min or max or all these kinds of things, right? So if I do data.tab, you can see I've got all kinds of stuff on this NumPy array. So what would it look like for us to implement sort of the naive dot product, right? So we're going to say, take our two arrays, multiply them together element-wise, and then add up together all those elements. And our naive dot product, that's actually slower than I expected it to be. That's closer to what that's still slower than what I'd expect, but interesting. I think the garbage collector is angry at me. Anyway, so this is taking me on the order, oh, no, sorry, this is expected. The next one will be faster. So this is sort of the naivest possible implementation. Turns out NumPy actually has a built-in for this. So if I just do array.dot array, now we're down, in 190, 160. Occasionally it gets up, 130. We're in, pretty close to the ballpark of the Fortran implementation. So if we come back here, that particular iteration is actually faster. So, both of these have some variance because of various things. If I made the arrays larger, we'd probably have a little bit more determinism here. But so the point of this, right, is we've switched out our data structures and suddenly we're competitive with Fortran. I would expect Fortran implementation to still be a little bit faster, but we're in the ballpark, and that's pretty exciting for us if we're trying to do high-level numerical programming in Python. Yep. Yes. Sure. Yeah. Totally. So coming back to that idea, so I mentioned that this array, one of the trade-offs we're making here is we're saying, okay, we're going to just dispatch on integer once instead of on every element of the array. So that's going to impose some restrictions on us, right? So in Python for our lists, we can just have sort of arbitrary random mixes of whatever we want in there. NumPy is going to be a little more stringent with us. So if I try to write a string into the array, it's going to yell at me. And it's actually yelling at me because it's trying to convert this string into an integer. So if I did like 0 here, it would happily accept that, which is a little sketchy. But at any rate, it will prevent me from writing anything other than an integer into the array. And when I did 0, it did write 0 in there. It's just, I would probably argue it shouldn't do that. We also can't grow an array. So once I create an array, it is of fixed size. So there is no append method on the NumPy array the way there is for a Python list. We can, however, reshape arrays. So this comes back to the question that you asked, which is that unlike lists, our arrays have a native notion of a shape and a dimension, right? So our base array was a one-dimensional array, but now we have a two-dimensional array. I've got a 2x2 array. And that lets me do things like slice, say, just the first element out of this, or just the first row, or just the first column, right? So all of these things suddenly become possible for us. So again, to sort of summarize the trade-offs we're making, NumPy arrays are fixed type, they are size immutable, they are multi-dimensional, and they are fast if you use them correctly. So let's go sort of one level deeper into the hood and talk about like how is this actually implemented? Like what is the data in this mysterious array object that makes this possible? So here I've got an array of 6 integers, and then I'm going to print some of the sort of important features of the array. So I'm going to print the D type, which is the piece of the array that tells us what kind of data it holds. I'm going to print the shape, which tells us how big is each dimension and how many dimensions are there. I'm going to print the strides, which tells us information about how we find each element in the array. And then I'm going to print the actual underlying data in the array. So ultimately, everything in your computer is just bytes. There are bytes somewhere, and it turns out the bytes here are in array.data.2bytes. Right, so I've got my array. It's of D type int64. It's of shape singleton tuple 6. So this is saying it is a one-dimensional array of length 6. The strides here, maybe it should be a little confusing at this point. So there's a single tuple with just 8 in it. And we'll come back to that in a second in a way that might make it make more sense. And then we've got this data, which is this like terrifying looking byte string, right? So we see like there's a 1 and then a bunch of zeros, and then there's a 2 and then a bunch of zeros, and then a 3 and then a bunch of zeros. And if we squint at it for a while, we might recognize that this is actually just the elements in our array. And this is just showing us in little endian order, because this is a modern CPU, the values, the underlying storage of our array. And if I change the D type here, so for example, I don't actually need 64 bits of storage to store these integers. I can say D type equals int 16, say. So now I'm going to use a smaller integer type to store these. And one thing we notice is that our strides shrunk, right? So it's 2, which is the number of bytes in an int 16. And we notice that there's less space between our numbers now, right? So this is saying that the first byte in my array is a 0. The second byte in my array is a 1. Or sorry, the first byte is a 1. Second byte is a 0. And this is just a way of representing the integer values in the array. Sorry, can you say that again?
In the matrix, when you take rows or columns,
yep.
Does it show in the same manner empty array?
In the same what? Sorry?
In the same way, does it show the rows and columns?
So here I just have a 1D array. Yeah. So say I come back here and I'll keep this in int 16, but I'm going to reshape this now. So I'm going to reshape this from being a 6 by nothing array into say a 2 by 3 array. So now I've got one row of length 3 and a second row of length 3, and then I've got 3 columns of length 2. And so one thing we'll notice is that our shape changed, right? We went from being 6 comma to being 2 comma 3. And our strides changed also. And so what it turns out this strides information tells us is how do I find a location or a value in the array? And in particular, what this says is that if I want to find the value at coordinate x comma y, then I need to multiply the x by the first element in the strides, and I need to multiply the y by the second element in the strides, add them up, and then take those as an offset from the underlying buffer here. Because buffers, memory in a computer is all ultimately flat. So if I'm modeling a 2D array, somewhere there has to be just like a flat array of integers somewhere, and I have to somehow say how I'm going to map the multidimensional aspect of my array onto that flat buffer. So what the strides are telling us here is that if I want to go down a row, then I need to move 6 bytes over in the array. And if I want to move over a column, then I need to move 2 bytes over in the array. Does that make sense? Cool. It's OK if that doesn't make sense. We've gone much lower level than most people care to go for many of these things, but I think this stuff is fun. So what are the core operations that NumPy provides? So we talked a little bit about arrays. We showed that dot product is fast. What else can NumPy get for us? So the first thing is ufuncs, which stands for universal function. So this is kind of related to the list comprehensions that we showed before for lists. So often we want to do something on an array, and we want to do it on every element of the array. And ufuncs allow us to do that in a way that's agnostic to the shape and size of the array. So here, for example, I have a 3 by 5 array. And I can multiply those together. And again, that's element-wise multiplication. So multiply is one of these ufuncs. If I have any 2 arrays, as long as they're compatibly shaped, I can multiply them together. There's also unary function. So I can take the square root of an array, which says take an array of the same shape and take the square root of every element of that array. I can also do comparison operators. So here I'm saying data modulo 3% means modulo. So this is going to give me values either 0, 1, or 2, depending on the remainder after dividing by 3. So this is going to give me a new array of integers, and then I'm going to compare all of those to 0. So Python lets me override this modulo operator, and it also lets me override this equality operator. And so this is going to give me back an array of booleans that tells me at each location in my original array, was that array mod 3 equal to 0? And I can combine those together, right? So I can take two Boolean arrays and I can AND them together. That's what ampersand here means. So I'm saying, give me all the locations in the original array that were divisible by 2 and divisible by 3. And as of Python 3.4, 5, Python 3.5, there's this new matmul operator. So the at operator is matrix multiplication. So I can take this matrix and multiply it by its transpose and get values back. And this is much, much faster than our naive Python operation. So again, to take a quick review, ufuncs provide efficient element-wise operations applied across one or more arrays. We've got arithmetic operators. We've got plus, multiply, divide. We've got comparisons, equal, greater, not equal, et cetera. Boolean operators. So if I've got two Booleans, I can AND them together. I can OR them together. I can XOR them. We've got trigonometric functions. We have transcendental functions. We have all the sort of standard mathematical things that you might want to do on numbers. So those were sort of things that we can do on the elements of an array. Often we don't want all of our data for some computation, right? We want to select some sub-piece of our data. There's various ways that we might want to do that. So NumPy also gives us a whole bunch of interesting different ways of selecting sub-pieces of an array. So here, just to give us some more interesting data, I've got an array of sine of just equal spaced values from 0 to pi, and the same thing cosine. So linspace here says give me equally spaced values, 10 of them ranging from 0 to approximately pi. And then I'm saying sine of that, and then I'm doing the same thing for cosine. So we should see this sort of go up and then go down and then go back up. Oops. Oh, I'm going to pretend I didn't do that. So I can, just like Python lists, I can index with a scalar, I get a value out. Sort of what we'd expect. I can slice arrays. So I can do sines bracket colon 3. This gives me the first 3 elements out of the sines array. There we go. Sorry, I keep inserting new cells instead of executing things. I can do colon 3, I can do 5 colons. This says, give me everything from 5 on. And I can do that same sort of every other element trick here. One of the very neat things about this is that these are actually 0 copy. So all of these slices did not make any copies out of the underlying data. All they did was create new views and mucked with those strides pieces that we talked about a little bit. So here, for example, when I do sines bracket colon colon 2, that's going to create a new array with the same baseline pointer, but twice as big strides. So it just says anytime you would have gone n distance, go twice as far. And that sort of turns out to be equivalent to just taking every other element of the underlying array. I think that's super duper cool. So we can index things. We can slice things. One of the most powerful things we can do is we can use Boolean arrays as predicates over an array, right? So I'm going to start with sines, right? I've got an array of sines. If I do sines greater than 0.5, I'm going to get a Boolean array of the same shape that tells me at each location in the original array whether that value was greater than 1/2. Right, so we see false, false as we start going up the sine curve, and then it gets true for a while, and then it goes back down. So now I'm going to say sines, and I'm going to index my sines array with sines greater than 0.5. This is going to say, take my original sines array, do that comparison to get me the Boolean array, which is going to tell me at each location whether or not I want to keep that value. So if I index my sines array with this Boolean array, it's going to say, give me all the locations where the indexer was true. And so as you can see here, I get sort of the middle chunk of this array. So the output here corresponds to this piece right here. So this lets us do all kinds of interesting things, especially when we start combining those with like the ampersand or operators. I can very tersely and very concisely express all kinds of predicates over my data, which is very nice. Huh? Yes, those do copies. I believe if you have like contiguous regions and then all falses, there's some cases where it will still figure out that it can do it as a slice. But I'm not 100% sure on that. So just printing sines to make sure we remember this. Another thing we can do is we might say, okay, I want, I don't have a Boolean predicate. I just want the values at this location and this location and this location and this location, right? So I might want to index with a list of integers or an array of integers that say I want the subchunk of the array, which is the values at all of these indices. Right? So here I'm saying signs, and I want the 0th element of signs, the 4th or the 4 indexed element, and the 7 indexed element. I'm not saying 4th because it's 0 indexed. And we can see we get value here, and value here. One of the things that this is really useful for, so you might ask, like, when would we want to just take a bunch of random indices and figure out, take chunks out of an array at those indices. So one of the things we can use this for is sorting. So say I've got some unsorted data here, right? I've got 1 and then 3 and then 2 and then 12. This is not sorted. This is the only interesting thing about this data. I can pass this to np.argsort. And what this is going to do is give me an array of indices that, if used as an indexer on the original array, would sort that data. Right? So you can think about this as a permutation, if you're sort of mathematically inclined, to apply to the original matrix to reshuffle that around. So I'm not going to change the shape. I'm just going to say take this and reshuffle it in accordance with these indices. So if I do unsorted data indexed with the sort indices, then now I have sorted data. Huh? Relatively speaking, yeah. I mean, so the nice things about this is because I'm passing it the whole array, NumPy knows how big the output array is going to be, so it can pre-allocate that, and then it can just zip around in the original array and copy them all over. So this is a copying operation now, but it's about as efficient as something like this could be, assuming that it's making a copy. This is particularly valuable when you want to sort one array by the order of another array. So this is a thing that we commonly do in tabular computations, right? Where I've got a bunch of columns of data, and I want to sort one column of data by another row, right? So I've got, a row of companies and a row of market caps, and I want to sort the companies by the market caps, right? So here I've got, market caps. Presumably these are in units of dollars, and I've got my assets that are just in alphabetical order. And now I want to say, what if I want to sort the assets by market cap? So I can say sort by mcap is argsort of the market caps, and then I can index my assets with that sorter. And this gives me the assets back in the order that they would be in market cap order, right? So for example, D is first. And if we look up here, we see that D has the lowest market cap of all these companies. So this turns out to be very powerful when you're doing, like, much of Pandas is implemented in terms of this kind of abstraction. When you say only limited up to 2 columns. So I'm only args, sorry.
So if you compare, their age, you get the gender out of demographic. So you have a filter of sort.
Yep. Yeah, so I'm only arg sorting one of the columns here. So I could apply this indexer to lots of other arrays, for example. There is, if I wanted to sort, say, by like one column and another column, there's another function that'll do it, which is np.lexsort. That says sort by this column, but use this column as a tiebreaker. Another thing we can use this for that's often valuable is aligning one piece of data with another piece of data. So a common thing that happens in time series analysis, especially in the financial sector, is I have data and I have some calendar, and my data doesn't line up with that calendar, right? So maybe I've got the trading calendar, like the NYSE calendar, and there's holidays in there, and there's weekends, and there's all these holes in it. And then I have data that came from some other process, right? I've got like earnings announcements, or I've got some other piece of data that's not necessarily tied to the NYSE calendar. So here I've got some event dates that are in January of 2017. They're just the 6th, the 7th, and the 8th. And I've got some values associated with those dates. And then I've got a calendar. And one thing that we might notice here is that the calendar has the 6th, but it doesn't have the 7th and the 8th. So if I had some other data that was aligned with this calendar, and I wanted to align my data with that, I would have to do something interesting. So one way that we might implement that is we can use this search sorted function. So this is a function that relies on the fact that you might have sorted data. And what this says is calendar.search sorted of event dates says take all of my event dates and find the indices where they would appear in another sorted array if I were to sort them in. right? So I've got 3 event dates, and I want to find their locations in the calendar. And then I can grab the associated dates from the calendar at that point. So here, if I do calendar bracket calendar.search sorted event dates, then what I get are the dates of my data forward filled to the next date that is actually in the calendar, which is, you might want to do backfilling or forward filling, and you could fiddle with the indices slightly to do that. But the thing that this is valuable for is if I've got 2 sorted arrays, I can very quickly align them together, and that turns out to be nice for certain things. Another thing we can do is we can do these selections on different indices independently. So I've got some 2-dimensional data. I can take the first 2 rows and the first 2 columns. And the way that I do this is I do the same syntax that I was doing before, right? So :2 just says give me the first 2 rows. And if I throw a comma in here, then whatever I do after the comma gets applied over the columns axis instead of over the rows axis. So this is saying give me the first 2 rows and the first 2 columns out of that array. Similarly, here I'm saying give me the first 2 rows and then give me the first and the last column, right? So I can mix these different modes of indexing. I can use a slice along one axis, and I can use a mask, or I can use an array of indices along another axis. And I can get fairly complex with these pretty quickly, right? So here I'm saying give me all the rows of the data where the first column of the data was even, right? So here I'm doing data, colon says I want everything along that axis. So :, 0 says give me the first column. Mod 2 gives me a Boolean array of is it either 0 or 1, depending on whether it's even or odd. == 0 converts that into a Boolean that tells me whether or not it was even or odd. And then finally, I'm indexing data along the first axis with that to give me all of those rows. So again, we can sort of compose fairly sophisticated algorithms in sort of pretty terse, and I think once you get used to it, pretty readable code, which I think is pretty cool. So just sort of to review NumPy selection operators. We've got slicing that works basically the same way as integers, except we have this, or same way as lists, except we have this extra feature of having multiple dimensions. We can use Boolean arrays as predicates over some axis. We can index with integer arrays to select indices along a particular axis. And if we index with a scalar value, we showed that briefly, that sort of takes a slice out along one dimension. So if I have a 2D array, I slice with a scalar, now I have a 1D array, which was just some particular layer of that original array. This one we're going to go through relatively quickly because I'm going slower than I expected, which is probably to be expected. So say I want to do reductions over an array, right? So I want to calculate variance. So I want to take every element of the array, subtract the mean, square all those, take the sum of those, divide by the length of the array. It is less important that you understand exactly the math and more that if you squint at the math and squint at the code, they kind of look like they might match. It's actually most math. And as sort of a sanity check here, if we take the variance of 1,000 samples from a standard normal, it should be about 1. So it looks like this has at least a prayer of being right. No, so there's no like list comprehension here or anything, right? So I said x.mean, so this is a scalar value, right? X.mean is a single scalar value. And I'm saying take the array and subtract a scalar value. So you should be a little bit suspicious about that, right? Because I took an array and a scalar, which are not the same thing, but I somehow made them work together. And we're going to come to that in just a moment. And then I squared that whole array element-wise. So again, I combine an array with a scalar value. You should be a little suspicious of that. We're going to take the sum of that whole array, and then we're going to divide that whole thing by the length. So one thing we notice here is we had some operations here that took an array and reduced it down by a dimension, right? We had an array, we took the sum of it, now we just have a scalar value. We had an array, we took the mean of it, we just have a scalar value now. So in the simplest case, these reduction operators take an array and reduce it to a scalar. Right? Take a range is just the NumPy array equivalent of the Python range, so this is just integers from 0 to 30. If I take the mean of that, I get a little bit less than half of 30. But we can do more interesting things with this when we have multidimensional arrays, right? So now I've got integers up to 30, but I've reshaped it into a 3x10 array. And again, this reshape operation is non-copying, which I think is interesting. So if I take the mean of the whole array, then that again essentially says flatten it and then take the mean. But I can also pass this axis argument to mean. So if I say take the mean along axis 0, now I'm going to take the mean over every column. Or I can take the mean over axis 1, which says give me the mean over all the rows. And if I had, by the way, I'm mostly showing two-dimensional arrays here because they're easy to read and easy to sort of think about, but these can be arbitrarily dimensional arrays. So I could take the mean over axis 75 of your like crazy multi-dimensional string theory data or something. That's really all there is for reductions. Many algorithms are implemented in terms of these, and understanding the axis piece is valuable. So reductions let us do efficient aggregations. We can do aggregations over single axis to collapse that dimension. There's lots of built-ins. So there's mean, sum, min, max, median, standard deviation. Basically, anything that you might plausibly expect to see is probably either in NumPy or in SciPy. Broadcast, and this is probably the most complex topic that we're going to talk about, so I'm not going to spend a ton of time on this, but if people are interested, this is sort of one of the things that can level up your NumPy understanding quite a bit, so feel free to come talk to me about this afterwards, and I'll talk your ear off for as long as you want. So here I've got a 1D array, which I'm going to think of as a row vector, and I've got a 2D array, but it's an n by 1 array. So I'm going to think about this as a column vector, right? So what should happen if I add a row vector and a column vector? Who has ideas on what this should do? Someone that's not Joe. All right, well, let's see what it does. So one thing you might think is that this should just crash, right? I don't know how to add a column vector and a row vector. Like, what does that even mean? But it turns out we can actually give this a nice semantics. And basically the way that we think about this is I've got a column vector, and I've got a row vector, and I'm going to sort of take the column vector and tile it across the row, and I'm going to take the row vector and tile it across the column, and then now I've got two arrays that are the same shape, and then I can just do my normal add them together thing. So in fact, that's what happens here, right? So I'm going to take my row vector and tile it along each row. I'm going to take my column vector and tile it along each column, and then I'm going to add those up together. It turns out this is actually the same machinery that is making array plus scalar work as well, is that a scalar gets promoted to a 0-dimensional array, and then it goes through this. So you can go, if you look on the NumPy docs, there's actually some pretty nice and not that complex rules about how this works, but it takes a couple minutes of just sort of like heavy thinking for you to get an aha moment, I found. So I'm not going to try to go through this in too much detail. This is a nice picture that I find sort of helpful for thinking about this, right? So if I've got two arrays that are the same shape, it's great. If I've got an array and a row, then I can sort of tile that row down and then add them together. And if I've got a column and a row, I can tile them together and then add them together, and that sort of works. But the main idea is to sort of have the geometric intuition, right? That if I have two arrays that aren't quite the same shape, but I could make them the same shape by sort of tiling them to match each other, then many algorithms just sort of fall out naturally from that. And so I'm going to claim that if you absorbed everything that I just talked about, then you are sort of ready to use NumPy in a pretty serious way. These are basically all of the core concepts that you need to be productive with NumPy and to use it well, I think. So just sort of to review what we just talked about. So numerical algorithms are slow in Python because the overhead of dynamic dispatch dominates our runtime, right? We're iterating over a list and checking if it's an integer. We're iterating over the list and checking if it's an integer. We're doing, iterating over our instructions saying, is it a binary add? Is it a load fast? Is it whatever, right? We're doing all these things over and over and over when very often we want to just do the same thing over and over. And when that's the case, we can use NumPy to make our code faster. So NumPy solves this problem of sort of oversaturated dynamic dispatch by imposing additional restrictions on the contents of arrays. And in particular, it does that by moving the inner loops of our algorithms into compiled C code. One thing to sort of note about this is that using NumPy effectively often requires sort of retooling or rethinking about an existing algorithm. Right? If you have an algorithm that's implemented in terms of a bunch of nested for loops, it often sort of takes a little bit of sort of restructuring to think about how to solve your problem. But I often find that the resulting solution in NumPy, when it's the correct solution, is like really clear and elegant and simple and sort of much more obvious. So I think it's worth the time often to think about how to solve a problem with NumPy, even if it doesn't immediately seem obvious how to do it. So great, right? NumPy, we have NumPy, we live in this sort of magical land of unicorns and rainbows. What else might we ever want from a numerical computing stack? So NumPy is great for lots of things. but there's some things that it doesn't support. So one thing that it doesn't support is we often have data that has some natural set of labels, right? We have dates associated with every row of an array, or we have stock tickers associated with every column of an array, or we have field names. We have like open, high, and low, and close. We might sometimes legitimately have more than one type of data that we want to keep together. And NumPy does have some support for this. There's this thing called a rec array, which kind of gives you an array of structs, but it's only good for certain kinds of things, and a lot of things in the SciPy stack don't really work well with rec array. So a common example here is I might have like some real value data and some categorical data, right? So I might have like prices of assets and sector codes, or prices of assets in their like the exchange that they trade on, right? And I might want to work with those in the same tabular data structure. Another thing is often, especially in the finance community, we have missing data, right? We have some observation that corresponds to some possible set of labels, but we don't actually have that value. And we need to somehow ignore or fill or otherwise work around the fact that we don't always have all the data that we might like to have. And so this is where Pandas comes in, right? So Pandas is a tool that allows us to kind of wrangle our unruly data even when it's trying to crawl away from us down the hill. There's a little more reasonable logo. So Pandas essentially extends NumPy with some more complex data structures. It also provides a whole bunch of utilities, which I'm not going to try to cover all of these, but it provides tools for input and output and data cleaning and rolling algorithms and plotting, all these kinds of pretty powerful things. But the good news is that I claim if you understand selection in NumPy, I think you basically understand selection in Pandas. So in Pandas, the analog of a 1D NumPy array is this series object. And the important thing to know about series is that there's actually really two pieces of it. There's an index and there's the values. And the values you should think of as the index you should think of as labels for the values. So whereas in NumPy, the only way we can talk about a value in an array is by its integer location in the array. In Pandas, we have two ways to talk about something. We can talk about the location where it is in the array, but we can also talk about the label at that point in the array. And so what that means is we now have two ways to index a series when we only really had one in NumPy. So in Pandas, we have these two axes. We have .loc and .iloc. So .iloc sort of matches the NumPy stuff that we were just talking about, right? So I do s.iloc 0. That's going to give me the first value out of the array. But I also have .loc, and .loc says, look up the value whose label is a here. And this is because a was the first label, it's going to give me the same value. And all of those slicing operators that we just talked about for a while with NumPy, all of those transfer over to both of these domains. So I can do .iloc:2, and this is give me the first two values out of the series. But I can also say .loc:(c), and this says give me all the values up until the label c appears. Right? So now I'm going to say give me all the values out of this. So we might contrast this to our Python dictionary before, right? Where a series, you can kind of think of it as like a hybrid of a Python dictionary and an NumPy array, where we have both the nice integer indexing as well as this label-based indexing. But one thing that we have in addition to the Python dictionary is we have a notion of order on our labels. So we can take advantage of that to talk about, say, slicing up until some value. Yes, it's inclusive. Yes. That turns out to be what you want most of the time for this, especially when you're working with time series data. But yeah, that is a point where you can sometimes run into gotchas, is that the integer indexing is exclusive. Again, indexing with arrays of indexes works just the way we'd expect. And Boolean indexing also works here. So if I have s, I can do s greater than 2, and that does the same sort of broadcasted operation. And then I can select all the values out of the array where the value was greater than 2. One thing that's a little bit interesting about this is that in NumPy, if I have an array of length 3 and an array of length 4, and I try to add them together, there's nothing that NumPy can reasonably do there. And it'll throw an error saying, these two arrays aren't the same, don't have the same shape. I don't know what to do. Pandas is a little bit more flexible. And so it'll look at the labels of your two arrays and try to align your values, and it'll fill in with nans when it can't align them. So here, before I had a series which was like A through E, and now I've got A, but I don't have a B. I have C, a D, and I have a Z in here, which we definitely didn't have before. Oops. And if I do my original series plus this new series, what I now get is a series with the union of all the keys that appeared in either of them. So they both had an A, so I summed both of their A values. But only one of them had a B, so now I just have nan. They both had C and D, and then they didn't both have E and Z. So depending on the context, this can be nice, or it can be a source of bugs. But it is often nice for sort of taking two arrays that are almost like indexed and combining them together and then doing something useful with them. You can also do things like SQL-style joins with these, where I can say, take the index of this thing and select all the subchunk out of this other one and then put them together into a table. And you can choose like inner or outer and all the different kinds of things you can do in SQL. And then there's also a nice sort of built-in functionality for filling those missing values. And in this case, we're just filling with 0, but if we had time series data, we want to forward fill, or we want to interpolate between missing values. And there's various options for how you can do the interpolation. The other thing that Pandas is really good at is reading data into memory. So Pandas read CSV, I think, has the most keyword arguments of any function I've ever seen. So there's something like, I don't know, there's more than I can count. So if you have a CSV that can't be read by Pandas, then you should just burn that CSV, because there's no saving that data. So here I'm saying pd.readCSV. I've got some historical prices from Apple. I've got OHLCV, and then this is from Yahoo, so they give me an adjusted close. And I'm telling Pandas I want to parse the dates column as a date, and Pandas is very, very good at parsing dates. And then I'm also going to tell it that date should be my index column. So rather than having it be a normal column, it's going to be a special label column. And what this gives me back is now not a series, but a data frame, which is the 2D analog of a series. And all of our slicing things, again, nicely generalized to multiple dimensions. So I can do iloc along 2 dimensions. I can do loc. And now Pandas is also very good at time series things. So I can give me the locations between 2 dates. And I want these 2 columns. All right, so I'm saying give me close and volume from February 1st to February 4th. Another thing that Pandas is really good at that's nice for finance especially is it has these really good rolling operations. I'm just going to let that GIF go through one more time. All right. So say I want to do a rolling mean of close and adjusted close, and it's a 5-day rolling mean, right? So the picture you should have in your head is I've got my 2D table. I'm going to take a chunk of 5 rows. I'm going to take the mean of those, collapse it down, and write it somewhere else. And I'm going to tick that whole thing forward and repeat. So I should end up with like 4 or 5 leading rows where it's maybe not clear what's going to happen because they're like off the edge of the table. And then once I get past that threshold, I should expect to just see sort of the rolling moving average. And in fact, that's what we see. So we get these leading nans. And there's actually some different parameters you can pass here to control what Pandas does with the leading values here. So here I'm saying AAPL.rolling of 5. And sort of what's interesting about this is that rolling of 5 is an expression by itself, right? So if I just do rolling of 5, I get this rolling object. And this has various methods. So I can do rolling 5 dot mean, or rolling 5 dot standard deviation, or rolling 5 dot select some columns, and then do a mean, say. The other thing that's very nice about this is Pandas data frame comes with a plot method. So I can take all this and plot these 2 columns. And it, out of the box, gives me a pretty good plot, I would say. There's not a lot I would do to change this around. So
for the rolling, you can have multiple sources. For example, you can have multiple CSV files.
yeah, so you might have different data frames, and you would roll on all of them, or so rolling by itself is a method of the data frame. So I have a given sort of table object, and I do a rolling transformation on that. But I could have, say, a list of data frames and do rolling things along all of those. Or if I have multiple CSVs, but they're really logically one, I might like concatenate them, or I might join them together. I would turn them into one table and then do a rolling operation along them. There's sort of various versions of these rolling operations that are specific to different contexts. So there's ones that know about the fact that we have time series data. So here I'm saying, take Apple, drop the volume column because it's too big, and it messes up the plot. And then I want to resample this down to weekly. So I'm going to say, take this in 2-week-long chunks, apply some aggregation to that, and then spit out all of those 2-week-long pieces. Right? So here, if we look at the dates, you can see that I get the 10th, and then I get the 24th, and then I get February 7th, et cetera, et cetera, et cetera. And I can control where the cutoffs are. There's like, if you want the intervals open or closed or half open, there's a whole bunch of parameters for resample. And again, I can plot this, which is pretty nice. Yep?
Question about the rolling. So it seems like, can you also define it as an object and then apply it to whole series of data frames?
So like the rolling object itself?
When you show just the rolling object itself.
So again, that was an object that I took. I had a data frame, right? So AAPL is just a data frame, right? And then I did AAPL.rolling of 5. So this rolling is associated with that original AAPL data frame. So I couldn't take this exact rolling object and apply it elsewhere, but I could just define a function that takes a data frame and does df.rolling5.whatever. So Python has very good support for functions as first-class values, and you can do all kinds of interesting things with those. But a given sort of instance of this rolling object is associated with a particular data frame. Does that answer your question? Okay.
The object that's created is data. It's not just pointers, it's data. So you can apply, it's like root bot. It's data from a specific data frame. So you can't really make it point to another data frame with a different structure and that would work.
Yeah, I mean, like you could go hack and like the rolling object by itself doesn't really have data. It's like, the way that I think about this is it's like a formula for performing some computation, right? So I've started doing a computation, but I haven't completed it yet. And I'll complete it when I say .mean. That will actually sort of materialize it. So I could probably take this and like find all of its internal attributes and like assign them around, but it's not designed to be done in that way in any sense. Yep. This one? Yes. Yeah. Yeah, so this is saying resample these in 2 weeks, so there's this whole complex system of like string keys that I can never remember what they are. So like 2W versus 1W. How did yeah, there we go. Or like I could do this 1 month, or I happen to know this because I was looking at this, like one for year is not Y, it's A. So some of these are not the most like super intuitive APIs, but they do work. So here I'm saying, give me the rolling average stuff year on year, which this is probably not that useful, but again, it's nice that Pandas has these time series aware algorithms. And again, it does these quite efficiently relative to the complexity of what it's doing.
So it's not just sampling there, it's actually taking the mean of all.
Yeah, so and there's different things I can do here. So I think I can do like .first maybe here. Yeah, so first says give me the first one in that block, or I can do like .max. So there's different aggregations. So the way to think about this is I have some data, I have some bucketing operation, and then I have some reduction along that bucketing operation. So this plot is a line chart, but this plot also takes roughly 1 billion parameters. So if I do, I'm actually just going to pop out here. So like if I have a data frame and I do df.plot, there's all kinds of stuff that I can pass to this. So one of the things in particular that I can do to this is you see this kind parameter. So I can say I want a bar chart, or I want a line chart, or I want a KDE plot, or a pie chart, or whatever else. So there's quite a lot of things that Pandas can do with that. And the other cool thing about that, which I have slides here that I'm probably not going to make it to, is that plot returns a Matplotlib figure, which I can then make further modifications to. So I might plot this and then take some extra data and put that on the same canvas, which can be valuable when you're building up a complex visualization. Cool. One more cool built-in operation is this EWM. So this is taking an exponentially weighted decay, or an exponentially decaying weighted blah. So this could be an exponentially weighted moving average. In this case, I'm actually doing an exponentially weighted standard deviation. And again, there's a bunch of these different operations that you could do. So here I've got so here I'm saying take the close, take the day-on-day % change. So this is calculating returns. Take the 30-day exponentially weighted moving average. Take the standard deviation along those. Take the 30-day exponentially weighted window, and then reduce that via the standard deviation operations. This might be a measure of volatility, for example. How am I doing on time? Okay, yeah, that's good. I'm going to breeze through these, but feel free to come up and ask me about it afterwards. So just sort of to summarize, I wanted to give kind of a sense of the flavor of the kinds of operations you might want to do with a real-world data set. So a couple weeks back, there was sort of a meme floating around Twitter, which was some well-known person had made a comment to the effect that millennials would be able to afford houses if they would stop buying avocado toast, which then caused a spate of people on Twitter tweeting graphs of the prices of various commodities priced in avocados, which most people might sort of look at that and kind of laugh it off. In the Quantopian Slack, this immediately caused us to say, how can we find point-in-time avocado pricing data? And it turns out the USDA has this. So if I go to projects, PyData Toolbox, notebooks, demos, avocados.py, I can scrape historical avocado pricing data from the USDA. My favorite part about this is that I'm hitting this URL and I'm telling it that the format is Excel, and this returns an HTML table, which is not particularly related to HTML or to Excel. So the main thing I want to show from this is that here I have different D types along the column. So one of the additional facilities that the Pandas data frame gives me is the ability to have different columns with different kinds of data in them. So within a given column, I'm still homogeneous. You can have object arrays, but you basically are back to Python performance at that point. But here, for example, I have date, which is a date time column, or I have number of stores, which is a integer column, or weighted average price and low price and high price. We actually can get like OHLCV data for avocados, which I think is hilarious. So I'm gonna pop out of the slideshow here, and just sort of to give you a sense of like what maybe a more complex analysis might look like in Python. So here I'm saying filter to just avocados whose variety is Haas, and then group by date and region and grab the weighted average price and take the mean of that and then unstack that and fill that and plot that. And what all this is going to end up doing is giving me day on day the average avocado price by region in the country and generate a plot of that. So it looks like avocado prices are actually pretty volatile. So one thing we notice here is that there's this organic here, right? So we basically, there's like 4 or 5 different, or there's a couple different categoricals associated with each avocado. So we have a region, we have a variety, which is either Haas or various green skin varieties, or I have organic, true or false. We might be interested, well, what's the spread on organic avocados, right? How much more expensive is an organic avocado than a non-organic avocado? And so here's a thing that does this. So I'm saying, say, give me the organic spread by region. So I'm saying, take a data frame, set the index to these 3 columns, which is kind of like doing a pre-computed group by, grab the weighted average price, unstack everything from but the date. So now I'm going to have basically a column for every unique region and whether or not it was organic. And then I'm going to have dates along my axis. I'm going to forward fill all of those because every day I don't necessarily have a quote from every kind of thing. Then I'm going to take all of that and group it by region. And then I'm going to apply this organic spread function. So one of the powerful things about group by is I can apply arbitrary Python functions if I have to. You pay a pretty serious performance hit for this, but if you're doing something complex and custom, it can still be a good idea. And so if I do the organic spread by region and plot it, we can see along each region the arbitrage opportunities for avocados. And what's interesting is sometimes organic avocados are actually cheaper. And then just for sort of more giggles, we can take this and build like a hierarchical covariance matrix of this. So I'm going to take the naive correlation of all these spreads. So if I'm imagining I wanted to say pair trade the different avocado spreads, and I'm interested in making sure that my different hedged avocado positions are uncorrelated with one another, then I might want to know some sort of like risk covariance matrix of the different avocado spreads. So I might take that and use Seaborn to generate a cluster map of the avocado spread. So we might notice that, for example, national, which is an aggregation of other things, is relatively highly correlated with other stuff, and in particular, it's highly correlated with the Northwest. So all the hipsters and millennials in Portland are buying all the avocados. And then just as another example, I talked about that these plotting things give me back Matplotlib objects, which I can manipulate and do work with just like any other Python object, so I can take this plot and I can rotate the labels, for example. So just to review very quickly, we talked a lot about Numpy. We talked a little bit about Pandas. So Pandas extends Numpy with more complex data structures and algorithms. I claim if you understand Numpy, and particularly if you understand Numpy selections, then you understand like 90% of Pandas. And a lot of Pandas' more confusing behaviors will make more sense to you. Like if you understand that like loc is just sort of a generalization of iloc that does label-based indexing, for example, was the thing that kind of caught me up for a while when I was learning this. Group by, set index, and unstack. I sort of showed some examples, but didn't give too much theory about how they work. These are really powerful tools, especially when you're working with categorical data. And finally, avocado prices are surprisingly interesting and surprisingly available on the internet. Thank you very much. Any questions before I head out? Yep.
Jump out of the mainstream and ask you to say a bit about the presentation notebook?
Yeah, totally. The fancy slideshow thing. So this is so the Jupyter Notebook has this notion of NB extensions, which are sort of snippets of JavaScript that you can install as Python packages, and then there's an extra command line argument you have to run to enable them. So this extension is by Damien Avila, who works at Continuum Analytics. It's called Rise. Damien. And what it does is you install it just like anything else, and then it gives you this little button here. And then as long as, the other thing you can do is you go to Edit, and you bring up this, you go to Cell. How do I bring this up? Yeah, so you go to Cell Toolbar, and you click on Slideshow, and that's what's giving me these little headings to define slides and subslides. So for a while, this was an extension, and it could take a notebook and generate a static slideshow from it, and you would serve it. It's using Reveal.js, which is a JavaScript presentation framework. But the more recent extension actually adds this button, and it basically takes the notebook and basically just like totally rewrites all the CSS and converts every cell into a slide. And it sort of works around, but it lets you sort of have still a live running kernel and do interactive things, which I think is pretty cool.
So say the name of the package?
It's Rise, R-I-S-E, and the author is Damien Avila. I'll make a point of putting that on the GitHub page that shows where it is.
Are you able to see what's coming next in your notebook?
No, there is an open issue about making that work. It's a little bit tricky. That works for the static version, but it doesn't work for the dynamic one.
Scott, so in this example, you are running your examples through Jupyter.
Yep.
Right?
Yep.
And I can observe that your data is staying in memory, and you can just add a random number, for example, array.
Yep.
It keeps on adding there. Eventually, if you are running a lot of records, like for example, CSV files,
Yeah.
large data,
Yep.
your compiler will eventually crash if you don't have a very big machine.
Sure. Yep.
So my question is, what is the best practice here when you clean up the memory if you host this in the application server?
Yeah, so there's a couple things you can do there. So this is a challenge we run into on Quantopian, actually. So we host a quite large Jupyter Notebook installation. One of the tools that we found valuable for that is just we wrote a little NB extension, much like this Rise one, that just shows people their memory usage. And so at least you can be aware of that. Like one of the things that's hard about that is you're doing stuff and all of a sudden you just run out of memory.
To look at your application, you have like 20,000 users accessing your information.
Sure.
Reading the dynamic records for stock market, for example.
Yeah. Yeah, so the notebook, unfortunately, is kind of a memory hog because it has all these like nice features for keeping values around. So for example, every time you execute a cell, if I do like x equals, or if I do like 1 plus 1, you can see this little in 150 here that's saying this is cell execution 150. And that actually binds a variable named _150, which is the value of that expression, which means basically nothing in the notebook ever gets garbage collected. You can turn that feature off. It's somewhere in IPython's configuration machinery, so that can help with this. The only other thing I really know is to restart your kernel periodically, which can be frustrating if you're doing large, expensive things. Maybe you can try to serialize intermediate results via, Pickle or HDF5 or something like that. The other thing is if you're doing just like large batch computations where you actually, like, you have more data than you can hold in RAM. There are fancier tools built on top. So I sort of opened this talk by saying there's all these fancy tools, and I wanted to come back to basics. If you do actually have more data than you can hold in RAM, you might want a fancy tool. So Dask is a very popular tool that's built on top of NumPy and Pandas, but actually, as it turns out, is a really cool sort of general parallel programming tool that you might be interested in.
So second question about data set. So right now, in this example, you're just loading the data directly.
Yep.
It's not dynamic. So for example, in your website, you have a sample data sets there that we can use
Yep.
for our testing.
Yeah.
What if we get an API coming from a financial source and get those dynamic records there and update the record immediately? So the Panda has support in terms of connectivity.
So Pandas doesn't have any notion of like network or like dynamically updating. Pandas is just basically a fancy array with some labels on top of it. So if you wanted something more dynamic, one of the things that's on Quantopian that you may be referring to is there's a tool called Blaze, which gives you sort of Pandas-like syntax. You can write these like array query expressions, but then it can actually can compile them to arbitrary backends. So you can take a piece of code that looks an awful lot like what's written in Pandas, but actually compile it into a SQL query. Or you can execute it in parallel with Dask. It has this notion of sort of front ends and back ends, and you can mix and match them. So Blaze is that sort of high-level expression compiler. If you're interested in that, the lead developer is right there. He's also a Quantopian employee. And then Dask is the like parallel programming thing that's a little bit more low level, but it's gotten very popular of late. And the author, Matt Rocklin, is a really bright guy and a really good speaker. Cool, thank you all. So, sorry, I got one more. Yeah, so I'll let me put the link back up there. So these will be up on github.com/ssanderson/PyData-toolbox. They're not up right now, so don't go looking at them immediately. But
notebook that you have is also there?
Yep, yeah. I'll put it up with all the other stuff, and I'll also tweet out a link to this that Scott B. Sanderson. Thank you all so much for coming out.